Hello? Hi.
Thanks, bro.
Okay.
Yeah, so feel free to start at like the 35. I'll wait outside and let people in, yeah?
Sure.
This is the front.
Yeah, I think we have, yeah. Can everyone hear me all right? Okay, cool.
What are you guys all studying? Like maths, data science, comp sci, active? I don't know what
Engineering.
Oh, I see.
Engineering, yeah.
So it's like, yeah, right, you guys all culture course, yeah. Did any of you guys miss the lab test, any of you guys? Because I have a friend who was like, okay, that's okay. Because if you don't miss the final, you're doing better than my friend. Last term he was like, making a salad or something. And I was like, oh, how was your math exam? He's like, and like, yeah.
Well, I'll go ahead. I think I'll go ahead and introduce myself. So I'm Lachlan. I'm going to be going through the first part of the lecture, everything up to sketching graphs with polar coordinates, and then Noah will take over and he'll go through integration and everything to the end of the course from there. I think we'll just wait a little bit longer. Okay, well, I'll go ahead and start. So, yeah? Okay, cool. So, I'm going to go ahead and begin with a really simple question, just to get us in the mood for maths. So, this is not that likely to come up in your exams, so I'm just going to quickly run through this and the techniques used to solve these questions. So generally what you want to do with these types of questions is you want to take cases. So you want to set out your solution nicely. So case 1. So the first case is when the inside of the absolute value function, so this is our absolute value function, is positive, in which case, because the inside's positive, we don't have to do anything to change the function to make it positive. So wherever 4x minus 5 is greater than 0, so in other words, x is greater than 5 on 4, then the absolute value of 4x minus 5 is just equal to 4x minus 5. All right, so then when we solve this inequality, which is greater than 3, it's just going to be wherever 4x minus 5 is greater than 3, right? And that's just wherever 4x is greater than 8, so x is greater than 2. And we just have to quickly check that x greater than 2 lies within our ranges of positive x values. In other words, is 2 greater than 5 and 4? And yes, it is. So this is a valid solution. And then we have to take our second case. So that's wherever the inside of the absolute value function is negative, in which case we have to multiply by -1 to make it positive again. So that's where 4x minus 5 is less than 0, so x is less than 5 on 4, in which case the absolute value of 4x minus 5 is equal to negative 4x plus 5. So when we solve this inequality, it's going to be negative 4x minus 5 greater than 3. So 4x plus 5 is less than negative 3. So x is going to be less than a half, right? And does that fit within our range of values? So is a half less than 5 on 4? Yes, it is. So this is another valid solution. So then the total set of solutions is just going to be negative infinity to a half, and from there we can go from 2 to infinity, right? So let's go ahead and move on to a little bit more of a challenging question. So we're going to be talking about the Epsilon-M definition of a limit at infinity. So the definition reads as, suppose we have L as a real number, and F is a real valued function defined for some interval from B to infinity. Then we can say that the limit at x approaches infinity equals L if for every positive number epsilon, there exists a real number m such that for all x greater than epsilon, then the function is within epsilon of the limit, right? So I'll quickly just draw a diagram to illustrate this a little bit better. So if we think about the graph of a function, that is approaching a limit, so limit L like this, what that means is that, well, first of all, like this expression here, it just means the distance between the function and the limit, right? So the idea is for every distance between the function and the limit, so every error bound between the function and the limit, epsilon, right? For the limit to exist, right, at infinity, it needs to be true that there always exists a value of m such that for all x greater than that m value, you're within that error bound of the limit, right? So let's go ahead and put that to the test by starting this question. So this is a pretty common question in Math 1131, Math 1131 exams. So it's good to know how to be able to do these ones. So let me just, can you go from here? Right, so what we're trying to do is prove that this limit is true. Right, so this limit, as x approaches infinity of x squared minus 2 over x squared plus 3, is equal to 1. So we're not trying to find the limit, it's already been found. We're actually just trying to prove that this limit is true using our Epsilon-M definition, right? So to start out these questions, it's good to write out the expression for the absolute value of f of x minus L. So that expression here is the absolute value of f of x minus L. So we want to simplify this a little bit. So what we can do is substitute our expression for f of x, right, which is just going to be x squared minus 2 over x squared plus 3, and subtract our limit, L, which is just 1, right? And then we can simplify this using a bit of algebra, right? So turn into 1 fraction. And what we get is those x squareds cancel out, and we're just left with the absolute value of negative 5 on x squared plus 3. We can notice that x squared plus 3, it's always positive, right? So therefore, we can get rid of those absolute value signs, and we're just left with 5 on x squared plus 3. So this here is our expression for the absolute value of f of x minus L, which is the distance between the function and the limit. But now what we have to do is prove that there exists that value of m such that wherever x is greater than m, this expression here, which is the distance between the function and limit, is always less than epsilon, right? So and so how do we do that? So the easiest way to do these questions is to be able to find m as a function of epsilon, right? Because as soon as we have m as a function of epsilon, for any epsilon value that we set, right, for any arbitrary value of epsilon, you're always able to come up with that m value because you have a rule that tells you how to get it from epsilon, right? So this is the end goal, right? As soon as we found m as a function of epsilon, we can say that the limit has to exist, right? But to get there, what we're going to do is we're going to have to look at our expression for f of x minus L, right? And see for which x values, so for what x values, is this true? Is this true? In other words, for what x values is the function only a distance of epsilon away from the limit, right? Is this true? And so what we can do, how can we do that? Well, we can just solve the inequality that we have, right? So we have 5 on x squared plus 3 less than epsilon. We want to see for what x values is this true? And right now the expression is not that simplified because we have that x squared plus 3. But we can just notice that 5 on x squared plus 3 needs to be less than 5 on x squared, right? Because by adding 3 to the denominator, sorry, let me just make that a bit clearer. By adding 3 to the denominator, we make it larger, right? So then by removing 3, then we make the overall expression, we make the denominator smaller and make the overall expression larger. So because this is true, wherever 5 on x squared is less than epsilon, it is also true that 5 on x squared plus 3 is less than epsilon, right? And therefore, it's also true that this distance between the function and the limit is less than epsilon, right? So let's go ahead and solve that inequality. So what we can do is we have this inequality here. So we have 5 on x squared is less than epsilon. So again, the question is, for what x values is this true? Well, we can just rearrange a little bit and see that wherever x is larger than the square root of 5 on epsilon, it is true that 5 on x squared is less than epsilon, and therefore it's also true that the distance between the function and the limit is less than epsilon as we require, right? And you can see here, because what was the original definition in the first place? The definition was, for any epsilon value that we want, it needs to be true that for all x values greater than m, the distance between the function and the limit is less than epsilon, right? So we can see clearly that wherever x is larger than the square root of 5 on epsilon, the distance between the function and the limit is less than epsilon, which we require, right? So a natural choice for m is just going to be the square root of 5 on epsilon. And because we found m as a function of epsilon, for any arbitrary epsilon value that we choose, we're always able to come up with that m value, and therefore the limit must exist. Right, so here, and therefore, by the Epsilon-M definition, which is, actually we should probably say, to conclude this question, it's better to say, therefore, wherever x is larger than m, so for x larger than m, f of x minus L is less than epsilon for any epsilon. right? And therefore, the limit as x approaches infinity of x squared minus 2 on x squared plus 3 must be equal to 1. Right, and so here's the solution written up quite nicely. So let's go ahead and move on to a question where we're actually trying to find a limit, not trying to prove that one exists. So let's go ahead. So the limit that we're trying to find is this one here. So limit as x approaches 0 of x squared, 3x squared, plus sine of x squared all over x squared. Oh, sorry, sine of 2x squared. So if you think about like the different techniques that we have to solve this limit, and it's pretty clear that you'll get a limit question in your Math 1131 or Math 1141 exam. But if you think about the techniques that we know to solve limits, like, does anyone have any ideas of what we could use to solve this one? Yeah. Yeah, we could divide by x squared, right? And that would give us, what? That would give us 3 plus sine of 2x squared over x squared divided by 1, right? And then we can clearly just pull that 3 out of the limit. And then now we're stuck with this limit here, right? And does anyone have any ideas of how we could solve this limit? Yeah? Yeah, you could use L'Hopital's rule. You could also just realize that it's really close to the standard limit. You know, sine x on x as x approaches 0, that's equal to 1, right? So like doing just a little bit of algebraic manipulation, right? Like multiplying and dividing by 2. So let's put that 2 out the front. We can see that we just essentially get the same limit as this one. And therefore this, whatever's inside the brackets, as x approaches 0, that will tend to 1. So then overall the limit will just be equal to 3 plus 2, which is 5. Yeah. Yeah, it's quite a standard result. If you want, you can use L'Hopital's rule, but I'm sure in Math 1131 and Math 1141, you can assume this limit. Yeah, so we're moving on from limits to looking at the properties of continuous functions. So we're starting off with a definition of continuity. And this one's pretty self-intuitive. It just says that a function is continuous at a point A if and only if the limit as the function approaches function approaches A of f of x is equal to the value of the function at that point. Just using like a little diagram, you can see why this has to be true. Like for a function to be continuous, right? As you approach a point from the left and right hand sides, you need to get to the value of the function at that point, right? If it was any other way, then your function would not be continuous. It would have a jump or a hole, and it would not be a continuous function, right? And moving on from that, we can look at the intermediate value theorem, which is just a consequence of how we define continuous functions. So it says that if f is continuous over a closed interval a to b, then, and again, if z lies between f of a and f of b, right? So there's a function value below and a function value above, and there's some intermediate value there, right? So z between those two function values. Then it has to be true that at least one point, the function crosses that line y equals z. In other words, there's at least one real number c such that f of c equals z. And again, this is pretty intuitive, right? If you have a continuous function, it can't have any jumps or gaps or holes or anything. So if that z value lies between two known function values, then the function must cross that line at least once, right? And that's the same as the intermediate value theorem. So let's go ahead and use those to look at a question. So this is from a past Math 1141 exam. So it says, consider a function f from its domain to the real numbers defined by this rule here. The first part is, what is the maximal domain of the function f, right? And then after that, we have to use the intermediate value theorem. so this is our function here. So we have a log function with, let's see, so it has an exponential inside and a trigonometric function. Let's see if we go there. Yes. Right. So the question is, what is A? So in other words, what is the domain of the function? So like when we're looking at this function here, there's a couple areas where the function will not be defined, right? We have a log, we have a fraction, so we should look for wherever, first of all, let's like look, the function is obviously not going to be defined wherever the denominator is equal to 0, right? So we can't divide by 0. So 2 plus cos pi minus x, it can't be equal to 0. And we also have a log function, right? And we know that the input to the log function needs to always be positive, right? So it needs to also be true, the domain is, or the values of x in the domain need to satisfy this equation, this inequality here. Pi minus x is greater than 0, right? So let's go ahead and just like quickly look at that denominator for a second, right? We have 2 plus cos pi minus x. We know that cos of pi minus x, it ranges between 1 and -1, right? Like any other standard trig function, standard sinusoidal curve, right? So if we add 2 to both sides, right, we're just going to get it ranges, between 1 and 3, right? And because it ranges between 1 and 3, well, first of all, we clearly know it's always non-zero, right? This expression here can never equal 0. And more than that, it's always going to be positive, right? So in other words, we don't have to worry about this first condition, and we don't have to worry about the denominator at all when it comes to looking at where is the input to the function positive, right? So in other words, the only thing we have to look at to find our domain is going to be the numerator. So that's going to be 2e to the x minus 1, right? So in other words, the domain is going to be wherever 2e to the x minus 1 is greater than 0, right? So just moving 1 to the other side, we just get e to the x is greater than 1/2, and then taking the log of both sides, x needs to be greater than the log of 1/2, which is also written as x is greater than -log 2, just using log laws. So we know that for our domain A, x needs to be always larger than the -log of 2. So let's look at what the question was asking again. It asked, what is the maximal domain A? So to conclude, we need to say what A actually is. And remember, A is a set. So we need to write it in interval notation. So it's going to be -ln2 to infinity, right? And x cannot equal -ln2 because log 0 is undefined. Yeah. Any questions with that? No? Okay, all good. Let's move on to the next part. So it says, by considering the intermediate value theorem, explain carefully why f of c equals 1 for some c in the domain of f, right? So let's just make a new page. All right, so we need to explain why f of c equals 1 for some c in A using the intermediate value theorem. Before we use the intermediate value theorem, there's one important prerequisite. Does anyone know what that is? Nope, that's all right. We need to be looking at, the function needs to be continuous, right? If the function's not continuous, then we can't apply the intermediate value theorem. So before we use the intermediate value theorem, we need to assure ourselves that the function is actually continuous, at least within its domain, right? So wherever x is in A, right, so in the domain of the function, so wherever x is, larger than -ln2, the function is always continuous because what we have is log 2e to the x minus 1. This is just a composition of continuous functions. So within its domain, so within x larger than -ln2, the function will be continuous, is continuous, because it's a composition of continuous functions. We write composition of functions. Perfect. So then now, now we need to actually apply the intermediate value theorem. So we're gonna, to actually like prove this, right? All we need to do is find two x values where the function is less than 1 and the function is larger than 1, right? Because in which case, if we can find those x values, then the function must cross at least one point the line y equals 1, right? Because we start below 1, we end up above it, or vice versa, right? So like we can just go ahead and sub in some points, some interesting points, and see what happens. Like if we sub in x equals 0, like what do we get? So f of 0 is equal to log of 2e to the 0 minus 1 over 2 plus cos pi, right? Cos pi is -1, so what we get is log of 1 on 1, which is log 1, which is just 0, right? So we know that f of 0 is equal to 0. Now let's just sub in another point. Like, let's say we sub in 1. Like, what do we get? We get the log of 2e minus 1 over 2 plus cos pi minus 1. Obviously, like, I can't just tell you what that is in my head, but if we sub this in our calculator, we get something roughly equal to, like, 1.112, which is clearly greater than 1. So we know that somewhere between 0 and 1, there needs to be that point where the line crosses, the function crosses the line y equals 1, right? Because we start below 1, we end up above it. The function is continuous. By the intermediate value theorem, there must exist at least one point where the function crosses the line, right? So therefore, because f of 0 is less than 1 and f of 1 is greater than 1, by the intermediate value theorem, there must exist, C such that f of c equals 1, right? And that's the question done. So let's go ahead and move on from properties of continuous functions to looking at differentiable functions. So looking at differentiability. So the question here is, if we have a function, a piecewise function, defined by this rule, and we know that the function is differentiable at the point x equals 1, we're trying to use that information to help us find the values of a and b, right? So we're going to have to use, at some point, the definitions of differentiability to help us out here. So let me just write out the function. So we have h of x is equal to, so we have a piecewise function, so we have ax squared plus 3x, and this is true wherever x is greater than or equal to 1. And then we have 2x plus b, and this is true where x is less than 1, right? So if the function is differentiable at the point x equals 1, right, we know that the derivative of each component of the function, they need to be equal at the point x equals 1. And the reason why is because if we just look at just like a little bit of, like a little diagram here, right? So we have, let's just say we had a piecewise function that looked like this, right? So in this case, the derivatives at the point, they do not match up, right? And you can clearly see that we have a cusp here, right? The derivative is not defined at this point, right? It's because if we look at what happens from the left side, as we approach from the left side, the gradient to the gradient of the tangent to the curve looks more and more like this, right? But if we look from the right side, the gradient of the tangent looks more and more like that, and we have a disagreement here, so it's not clear what the derivative should be, right? And we have a cusp. So because the function is differentiable at the point x equals 1, we need it to be true that the derivatives of these two branches of the function are equal, right? So the derivative of this top function is just using power rule, 2ax plus 3. And the bottom derivative is equal to 2. So we need this to be true, right? So and this is true at the point x equals 1, so we can just sub that in. So we know that 2a plus 3 equals 2, and therefore 2a equals, what, -1. So then a is equal to -1/2. So we know that a equals a -1/2. And we used the fact that the function is differentiable to help us find that. However, we still haven't actually found b, right? We've only found a. So what information can we use to help us find b? Does anyone know? Yeah? Exactly, right? It needs to be, the function needs to be continuous at the point as well. So at x equals 1, function is continuous. It's continuous. So therefore, so that means, in other words, the left and right hand limits of h of x, right? So as we approach from the left and we approach from the right, they need to be equal to whatever the value of the function is at that point. Just using the definition of continuity that we went through earlier. So clearly, like if we look at the left-hand limit, so the limit as x approaches 1 minus of h of x. If we're approaching from the left side, we're going to be looking at this branch of the function, and this limit is just going to be equal to 2 plus b, right? And this needs to be equal to the value of the function at the point. We know that h of 1, right, because 1 is actually inside here, we know that h of 1 is equal to whatever this is, where x equals 1. And because we found a, that's just simply going to be, a half plus 3, which is just 5 on 2. So in other words, 2 plus b must be equal to 5 on 2. And that gives us b equals a half. And that's the question done. So we found the values of a and b. Any questions here? Nope. Yeah. So this is the solution. I've written it up in LaTeX. It's nice. So let's go ahead and move on from differentiable functions to looking at the mean value theorem. So the mean value theorem. So the mean value theorem states, so we have a continuous function on a closed interval a to b, and the function also needs to be differentiable on the open interval a to b. So the theorem says that there exists at least one real number c inside that open interval where f of b minus f of a over b minus a equals f dash of c. And you know that this is just saying that at some point the gradient of the tangent to the curve is equal to the gradient of the secant from b to a, right? Just a quick diagram. So if I just had a function like this, for example, this is, say this is a, sorry, this is b, that's a, this is our secant, and there exists a point c where the gradient of the tangent is equal to the gradient of the secant, right? And a common application of the mean value theorem and a common place where mean value theorem questions come up is asking us to prove inequalities involving functions using the mean value theorem. And so this is pretty common for both MATH1131 and MATH1141. So it's good to know how, it's good to be able to know how to do them. So this question here says we have a differentiable function f on the real numbers such that its derivative is always less than or equal to 1 for all x in the real numbers, right? So we know that f of 2 equals 2, and also that the function is, and then we're trying to use that to prove that the function is always larger than or equal to x, right? For all x less than or equal to 2. So now the question is asking us to prove that the function is always larger than or equal to x for all x less than or equal to 2. So it makes sense for our interval of values to choose, right? Because remember, to use the mean value theorem, we need to consider a certain interval. It makes sense that the interval that we would like to consider is just going to be x, starting from x and going up to 2, right? Because we know x is always less than or equal to 2. And also we're trying to prove that the function is always larger than or equal to some, larger than or equal to x. So it makes sense that because we have an f of x here, right? It makes sense that our lower bound should be x, right? So before we use the mean value theorem, again, we have to be sure that we meet the requirements of the mean value theorem. So that's, again, the function needs to be continuous on the closed interval and differentiable on the open interval. Luckily, we know that's true because they said in the question the function is differentiable for all x. And if it's differentiable for all x, it's continuous for all x. So therefore, continuous, differentiable, and we can apply the mean value theorem. So applying the mean value theorem on this specific interval here gives us f of 2 minus f of x divided by 2 minus x. This is equal to f dash of c for some c in x to 2, right? And because c is a real number, and given in the question it says that the derivative is always less than or equal to 1, like this part of the question, we know that f dash of c also needs to be less than or equal to 1, and that's where we sort of get that inequality in, and we're just going to do a little bit of algebraic manipulation to help us prove the final inequality, right? So we know that this here is always less than or equal to 1, all right? So this fraction f of 2 minus f of x divided by 2 minus x, that's always less than or equal to 1. So just moving that to the other side, we get f of 2 minus f of x. That needs to be less than or equal to 2 minus x, right? How are we going to get rid of f of 2? Well, it's given in the question that f of 2 equals 2, so we can just go ahead and put that there. So again, 2 minus f of x is less than 2 or equal to 2 minus x. We can cancel 2 on both sides, so negative f of x is less than or equal to negative x. And therefore, multiplying by negative 1, we need to remember to flip the sign of the inequality. So therefore, f of x is larger than or equal to x for all x less than or equal to 2. And the question is complete. So with these types of questions, when we use the mean value theorem to prove inequalities, there's a couple important things we have to keep in mind. Again, before we use the mean value theorem, we need to assure ourselves that we have met the requirements of the mean value theorem. So again, it needs to be continuous on the the closed interval and differentiable on the open interval. Yep. So make sure you do those. Make sure you state that. So yeah. So a consequence of the mean value theorem is L'Hopital's rule, which we can use to evaluate limits. So you all know L'Hopital's rule, but quickly, if we have a limit, we're trying to find a limit of the form f of x over g of x, and this approaches an indeterminate form, so either 0 on 0 or infinity on infinity. We can find this limit just simply by finding the limit of the derivative f dash of x divided by g dash of x. And again, like the mean value theorem or all the other theorems that we've looked at, before you apply L'Hopital's rule, you need to show that it does actually approach an indeterminate form. You can only use L'Hopital's rule if it does sort of approach either 0 over 0 or infinity over infinity. Otherwise, it's not going to work properly. So let's go ahead and apply L'Hopital's rule to an interesting question I took from Math1131 exam. So it says we need to find this following limit using L'Hopital's rule, and then using that, determine whether this function is differentiable at the point x equals 0. All right, so let's go ahead and start this question. So they asked us to find this limit here. So the limit as h approaches 0 of e to the negative 1 on h squared divided by h. So it's already in the form of a fraction, right? This is already the form of like f of x divided by g of x. So like the most intuitive idea is firstly check whether we can use L'Hopital's rule. So like quickly subbing in 0, like e to the negative 1 on 0, that approaches e to the negative infinity, which approaches 0, right? And obviously as h approaches 0, h approaches 0. So this does actually approach 0 over 0, so we can use L'Hopital's rule in this case. So using L'Hopital's rule, like we differentiate the top and differentiate the bottom. So using the chain rule, the derivative of the top, so the derivative of negative 1 on h squared is going to be 2 on h cubed, and multiplied by the original function, and then we're just dividing by 1 the derivative of h. So now we're trying to find the following, L'Hopital's rule says this following limit here is equal to the original limit. Let me just write these in. Right, so like, what is this limit going to equal? Okay, let's think about what happens as h tends to 0. Well, the top, again, tends to 0. The bottom tends to 0. We tend to 0 over 0. And so we have two options. We can either apply L'Hopital's rule again and see what happens, or we have to go back to the drawing board. And if you just think about what happens if you apply L'Hopital's rule again, well, you're actually going to get another function of the form, I don't know, some constant times e to the negative 1 on h squared divided by h to the something, which is going to continually approach 0 over 0. So if we use L'Hopital's rule again, we're going to get to a point where we have to use L'Hopital's rule again, and again, and again, and again. And it's not going to take us anywhere. So we do have to go back to the drawing board because it's not going to work. We have to think of another method. So let's go ahead and take another look at the question. What does it say? It says, using L'Hopital's rule, find this limit. Right? So we know that L'Hopital's rule is the right idea here because we have to use L'Hopital's rule in the question. But we applied L'Hopital's rule to the original function and it's just not working. So then, what do we do from here? Well, we notice that we have a fraction, right? And our first thought was to just use this and then apply L'Hopital's rule. Differentiate the top here, differentiate the bottom. But that didn't work, right? But what we can freely do is simply rewrite this expression, right? So we have the expression e to the negative 1 on h squared divided by h. Well, we could flip the top and the bottom to get a new fraction that's, it's equal, but obviously it looks different. So we can take h to the negative 1 on the top here, and then we have e to the 1 on h squared. So what we did was we didn't change anything, but we changed how it looked, right? And we also changed what the derivative of the top and the derivative of the bottom are, right? By doing this step here, we've actually changed, the top derivative is different, the bottom derivative is different. So then maybe L'Hopital's rule will work now that we flipped it. So now the derivative of the top, it's going to be negative 1 on h squared. The derivative of the bottom, it's going to be, negative 2 on h cubed e to the 1 on h squared. All right, now we can get rid of those negative signs, multiply top and bottom by h cubed. So we get h on e to the 1 on h squared. And now let's see if this limit can be evaluated, right? Well, as h tends to 0, the top tends to 0. What about the bottom? So we have e on 1 on h squared. As h tends to 0, this approaches e to the infinity, which approaches infinity. So we approach 0 divided by infinity, which will approach 0. So then the limit, we know that the limit must equal 0. So this limit is just equal 0. And that's the question. So I think the main idea with this question is that sometimes if L'Hopital's rule doesn't work, but we know that it's the most appropriate strategy, we can just simply flip the top and the bottom, and then we'll get new expressions for the top derivative and the bottom derivative. And it might actually work in the end like it did for us here. But we're not finished with the question yet. It also asked us to determine whether the function is differentiable at x equals 0. So to determine whether a function is differentiable depends on whether its derivative is defined at that point. So what is the derivative again? Using first principles, right? If we have a function f of x, its derivative will be the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And this is just sort of rise over run idea. All right, so what we're trying to do is show that h dash of 0 exists, right? Because if h dash of 0 exists, then the function h of x is differentiable at the point x equals 1. Right, so it's not h of x, it's f of x. Show that f dash of 0 exists. All right, so we know that f of x was defined by this rule. So e to the negative 1 on h squared for h not equal to 0 and 0 for h equals 0, right? Oops, not h, x. x, right? So then, well, what is the derivative? F dash of 0? Well, we can use first principles, right? So we know that f dash of 0 is going to be the limit as h approaches 0 of f of 0 plus h minus f of 0 divided by h, right? F of 0, we know that it's equal to 0, like using our function here. So then, therefore, it's just going to be f of h divided by h, and this is we're looking at the limit as h approaches 0. And let's just add a new page. Right, so then the limit as h approaches 0 of, well, f of h is e to the negative 1 on h squared, right? Because h is not equal to 0, right? It's tending to 0, it's not equal to 0, so we just use this non-zero component of the function. And then we divide by h, and what we get is this limit here. And this is exactly equal to the limit that we proved in the previous part. We know that's equal to 0, right? So therefore, f dash of 0 exists and equals 0. Therefore, f of x is differentiable at x equals 0. Does anyone have any questions here? No? Okay, let's move on then. So, yep, there's a solution. All right, so we're done with L'Hopital's rule and the mean value theorem. So let's move on to inverse functions. So a bit of theory before we move on to the questions. So suppose that f is a one-to-one function, right? Then there exists its inverse, which is a unique function where the domain and range are swapped. And then now we have the inverse function theorem. It says if I is an open interval and the function f goes from I to the real numbers, it's differentiable, and its derivative is always non-zero, then f is one-to-one, and it has an inverse function. So in other words, the function f is invertible. Then we also know that its inverse g is differentiable at all points in its domain. So the domain of, remember, the domain of g is the range of f. And also, we have a handy formula for the derivative g dash of x, right, of the inverse. And yeah, so I think quickly I'll just draw a little diagram that I think helps make this formula make a bit of intuitive sense. Like if we just have a function, right, f, it looks like this. Then remember its inverse is going to be reflected over the line y equals x. So if we think about the gradient to the tangent at a point, right, so we're just looking at secant here. So this is a slight change in x, and this is the resulting slight change in f. For the inverse, right, if we look at a change in x, and a change in the inverse function, we can see that these things are just the same lengths, but just swapped, right, just flipped. So therefore, because we know that, the derivative f dash, it's roughly this, right? And we know that f inverse dash is roughly this. And we know that delta x2 is equal to delta f, and delta f inverse is equal to delta x1. So this is roughly the same thing as 1 on f dash, right? So that's why this formula makes a bit of intuitive sense. All right, so let's use that information to move on to a question. So again, I took this from a Math1131 exam. It says we have a function f, and its domain is 0, not inclusive, up to 2 square root pi, and it goes to all the real numbers. It's defined by this rule here, x squared plus cos x squared. So the first part of the question is pretty straightforward. It says, let's find all the critical points of f and determine their nature. So critical points, let's remind ourselves of what a critical point is again. A critical point is anywhere where f dash of x equals 0, or it's not or a point where it's not differentiable. we know that this function is going to be, it's going to be differentiable, you know, in its domain, so we don't have to worry about that second part. We're just going to look for wherever f dash of x equals 0, and then we have to try find the nature of those points. Yeah, so let's go ahead and check that out. So we know that f of x equals x squared plus the cosine of x squared. Just applying various differentiation rules, like this is just going to be 2x. Using chain rule, this is going to be 2x. And then derivative of cos is negative sine, so negative sine of x squared. So this gives us in the end 2x minus 2x sine of x squared. Right, and we can just quickly factor out that 2x, and we get 1 minus sine of x squared. So now we want to solve for wherever f dash of x equals 0. So that means, you know, where 2x, 1 minus sine of x squared equals 0. We said that x, like the domain of f, x is not in the domain of f, so x equals 0 is not a solution. So to find our solutions, we're going to be looking for wherever sine of x squared equals 1. Right? So in other words, we want to solve for wherever x squared, you know, equals pi on 2, 5 pi on 2, 9 pi on 2, etc. Notice that we had x, this is our domain, right? X is less than 0, sorry, x is larger than 0 and less than or equal to 2 square root pi, I think. Yep. So that means x squared is less than 4 pi. So then therefore, that's not a solution. Everything larger than that is not a solution. These are our only two solutions that fit within our domain. So therefore, we get critical points at x is equal to the square root of pi on 2 and x equals the square root of 5 pi on 2. But we're not done yet. The question did ask us to determine their nature. So let's go ahead and determine their nature using, let's say, the second derivative test, right? So we know that the first derivative is equal to 2x minus 2x sine of x squared. So it's a bit painful, but we can differentiate this again. So using product rule, that's going to be 2 minus, okay. Let's take the 2 out. So we have the derivative of x sine of x squared. So left, so we keep the left untouched. And now the derivative of sine of x squared is going to be 2x sine of x squared. And then now we go here, we add, leave sine of x squared untouched, and then differentiate x, we get 1, right? So therefore our derivative will be, we can take 2 as a factor out, and we get 1 minus 2x squared sine of x squared. Oh, so that's not sine, that should be cos. Cos of x squared plus sine of x squared. So now we can put in our points. So we know that x squared equals pi on 2 and 5 pi on 2. All right, so if we plug that in, what we get is f dash of the square root of pi on 2 is equal to 2, 1 minus, okay, we know that cos of pi on 2 equals 0. We also know that sine of pi on 2 is equal to 1. Okay, actually, let me just check this quickly. Sorry, this should be a negative here. Yep. So that should be minus 1. And so what we get is 2 times 0, which is equal to 0. So we plugged it into the, sorry, that should be second derivative. We plugged it into the second derivative, and it's also equal to 0, so we know that it's a possible point of inflection. But we can't, we have to quickly test whether it actually is a point of inflection. So we'll go ahead, we have to use the second derivative test for points of inflection. So this is here. So at the point, the square root of pi on 2, and then we look at the neighborhood of points around it. So a point that's a little bit to the left, a point a little bit to the right. I'll save ourselves the time of having to actually put this in our calculators. We get that it is actually a point of inflection, so we know that it's a point of inflection. But I encourage you, if you want to do that yourself. Likewise, the square root of 5 pi on 2 is also a point of inflection. So therefore, our critical points are the square root of pi on 2, the square root of 5 pi on 2, and both are points of inflection. So wherever the parts of the function that change concavity, right? So we found all critical points of f and we've determined their nature. Now we need to explain why f is invertible, and then state the domain of its inverse, and then hence find f inverse of 5 pi on 2. Right, so why is f invertible? So let's go ahead and remember, for a function to be invertible, if it's 1-to-1, then we know it's invertible, right? So if we could show that f of x is x like 1-to-1, then therefore, we can conclude that it's invertible. So by just looking at f of x equals x squared plus the cosine of x squared, we know that f dash of x is equal to 2x, 1 minus sine of x squared. Well, we know that sine of x squared always lies between negative 1 and 1. Therefore, 1 minus sine of x squared, 1 minus sine of x squared, that's always going to be positive. Therefore, we know, and because x is always larger than or equal to larger than 0, we know that the derivative is always greater than or equal to 0. Right, so we know that the function is continuous, its derivative is always greater than or equal to 0. If we look at the graph of the function, it's going to be increasing. It's going to look something like this, right? Because we have those points of inflection. But the function always remains 1-to-1, right? Therefore, we know that it is and invertible. And thus invertible. So the function is invertible, but the next part of the question was asking us to state the domain. So remember that the domain of the inverse function is the range of the original function. So it might be a bit annoying, like what's the range of x squared plus cosine of x squared? Well, we know that the function is 1-to-1, so the minimum point of the function needs to be at the bottom left corner, right? So we can find the minimum just by substituting 0 in. Obviously, the function actually never attains this minimum because x doesn't ever equal 0, but this will act, roughly as the minimum for the function, so the smallest value that it could attain. Just substituting that in, we get 1, right? Because cosine of 0 is 1. Oops, let me just write this a bit better. So f of x equals this. So f of 0 equals 1. Also, the maximum, global maximum of the function will be at the farthest right point. So when we substitute 2 square root pi in, so what we get is 4 pi plus the cosine of 4 pi, which is just, cosine of 4 pi is just 1, so it's just 4 pi plus 1. So therefore, the range of f, remember it doesn't actually attain this value, so this will be a closed bracket, so open bracket, and then, but it does actually attain that maximum, so this will be a closed bracket here. So this is the range. Therefore, for the inverse function, so the domain of the inverse function, it's just going to be this thing here. So it's going to be 1, 2, 4 pi plus 1. Perfect. And then we're not done yet. It also wanted one more thing. It wanted us to actually find what f inverse of 5 pi on 2 is. So f inverse of 5 pi on 2, I think that's it, yep. F inverse of 5.2. Okay, perfect. So F inverse of 5.2. Well, we don't actually know what F inverse is. We never actually found what F inverse is. And looking at our function, I don't think we want to. It's not going to be pretty, right? So instead, we can consider, well, finding F inverse of 5.2 is the same thing as solving for what value of x does f of x equal 5.2, right? So what's f of x? X squared plus cos of x squared. And we want to see where does that equal 5.2. And we can quickly just make a substitution. Let's say u equals x squared. So then we're trying to solve for u here, u plus cos u equals 5.2. So does anyone have any ideas? Is there a quick way we could solve this? Yeah?
Could you just say like posit that u equals 5.2?
Yeah, clearly, like, if you just think about it for a second, like, you can use inspection, right? If we put 5.2 in there, like, cosine 5.2 is 0 exactly, and then we just have u, 5.2. So exactly right. So u is equal to 5.2. So therefore, x equals the square root of 5.2. And we can go back here and then say f inverse of 5.2. That's just equal to the square root of 5.2. Perfect. And that's that question done. So let's move on to the next part. So now we have to find where is f inverse of x differentiable. So for this one, we're going to have to use the inverse function theorem. So let's go ahead and look at the inverse function theorem. So it says that, remember the inverse function theorem said f inverse, so the derivative of the inverse function, is equal to 1 over f dash of f inverse of x. Right? So clearly this derivative is not defined wherever the denominator is equal to 0, right? And wherever the derivative is not defined, then the function is not differentiable at that point. So we can just think about solving wherever f dash of f inverse of x equals 0. So remember what f dash of x was? It was 2x 1 minus sine of x squared. And so, okay, immediate solution, if f inverse x equals 0, then the function is not defined, so the derivative is not defined. But f inverse of x, remember that the domain of f of x was this. So then the range of f inverse is the same thing, and it never equals 0, so that's not a solution. So now we just have to look at wherever sine of f inverse of x squared is equal to 0, right? So in other words, wherever f inverse of x is equal to, let's go ahead, wherever it's equal to the square root of pi on 2 or square root of 5 pi on 2. And I got that just by looking at, sorry, not 0, that should be 1, my bad. You just get that from solving, this sort of thing, sine of u squared equals 1. So wherever f inverse of x equals the square root of 5 pi on 2 or the square root of 5 pi on 2, then the derivative is not defined. And from the previous part, remember, we found that, wait, let me check. Yeah. Oh, whoops, sorry, my bad. This is not. I just made a quick mistake. Let me just check what I did wrong. Oh, yeah. Sorry. No, this is right. My bad. It should be wherever f inverse, oops. should be wherever f inverse of x equals square root pi on 2 or square root 5 pi on 2. So in other words, we're trying to solve for where, so now we just look at, x has to be f of the square root of pi on 2, and f of the square root of 5 pi on 2. And this just occurs, we can just substitute that into our original function, which was f of x equals x squared plus cos of x squared. If we put in the square root of pi on 2, we just get cos pi on 2 equals 0. We just get x equals pi on 2 and x equals 5 pi on 2. So the question, the beginning of the question said for us to find wherever the function is differentiable. So clearly the function is differentiable for all x in the domain of f inverse. The domain of f inverse was 1 to 4 pi plus 1. But x cannot equal to pi on 2 or 5 pi on 2. And that's our solution there. Any questions? Okay, cool. So that's the end of inverse functions. So the last part that I'm going to go through is just quickly going through curve sketching, doing oblique asymptotes. It's I guess it's a fairly common question in exams, graph some sort of function that has an oblique asymptote. So quickly, the definition just says we have an oblique asymptote wherever the function approaches the line in the limit as x approaches infinity. So let's just put that to the test by actually just doing a question. So we're trying to sketch the following curve. 3x squared minus 4 over x plus 2. So before, to actually sketch this curve, we have no information now, so we have to find information. So the first thing we could do is look for intercepts, right? So our x, y intercept. We can find asymptotes. That will help us. We can also look at where the function is positive, negative, and it can also help to find turning points. Right, so in general, when you do these questions in exams, it's good to just think about what you need to find, what information you need to find before you can then graph it. So let's go ahead and look at, first we can just do intercepts quickly. So we know that we have a y-intercept where x equals 0. So x equals 0, we just get negative 4 on 2. That's just negative 2, right? So that's our y-intercept. So we write that out. Our x-intercept is wherever this is equal to 0. 3x squared minus 4 over x plus 2 equals 0. The denominator it doesn't contribute here, so it's just looking to solve for wherever 3x squared minus 4 equals 0. In other words, x squared equals x equals plus minus 2 on root 3. Right, so that's our x-intercepts, right? So we know our intercepts with the coordinate axes. Now let's go ahead and find our asymptotes. So asymptotes, well, clearly there's a vertical asymptote at x equals 0, right? If the denominator is equal to 0, then we'll have a vertical asymptote. So x equals negative 2 gives us our vertical asymptote. Now what about oblique asymptotes? Remember this definition here. So it said, in the limit as n approaches infinity, to find our oblique asymptote, it's just the same thing as seeing whether the function approaches a line in that limit as x approaches infinity. So in other words, if we could write the function, so we currently have a quadratic over a, we currently have a quadratic over a linear function. If we could have a linear function here plus some other function that approaches 0 as x approaches infinity, then as x approaches infinity, we'd approach that linear function. In other words, we'd approach a line, so we'd have an oblique asymptote. So in other words, to find our oblique asymptote, we can just try rewrite this expression here. So our expression is 3x squared minus 4 over x plus 2. So to rewrite this expression, what we want to do is sort of build up like x plus 2's on the top. In other words, what I mean by that is we have a 3x squared here, right? This is very close to 3x squared plus 6, which is 6x, which is the same thing as x. Factoring out 3x, we get x plus 2. And it's handy because we know that we could cancel that x plus 2 by splitting the fraction, right? But if we add plus 6x, then we need to subtract 6x, right? So let's write this out. So if we add 3x, we need to also subtract it to maintain equality. Okay, so subtract 6x. But now, when we do this, right, if we stopped here, then we get x plus a linear function over a linear function. And the thing is, this linear function does not approach 0 in the limit, so we have to do a bit more manipulation. So what we want to do is then, we see this minus 6x minus 4. Well, that's very close to negative 6x minus 12. And the reason why I'm doing that is because I know that I could factor out a negative 6 here and I get an x plus 2, which then I could then cancel by dividing across by x plus 2. So if I make that a minus 12 up here, I need to add 8, right? By adding 8, then I go back to our original expression. So I haven't changed anything, but now I can factorize this. I can take out factors of x plus 2, and then I'm able to cancel them out and get the expression that we want, that we desire. So minus 6, x plus 2, plus 8, right? So in other words, we get this here. So this is our expression for the function. And clearly, as x approaches plus minus infinity, right, the 8 on x plus 2 term tends to 0. So we just tend to the line 3x minus 6. So that's our oblique asymptote. I wouldn't say that I'm ready to graph yet because I still need to have a bit more information. So what I can do is look at the main points that we have. So we have, if this is the origin, right, we have our axes, our x-intercepts. Whoops, this is going to be plus 2 on root 3. This is going to be minus 2 on root 3. And this is going to be the asymptote at negative 2. So let's just sub in values into our calculator to sort of see if the function is positive or negative in these regions, right? So in this region between 0 and 2 on root 3, just substituting into our calculator, we can see that this region here, I'll just save us some time and I'll actually do it. This region here, it's going to be negative. Likewise, this is also negative. Oops, wait, this should be, oh, sorry. This is going to be negative as well. This is going to be positive here. And this is going to be positive here. I'll just circle these. It's a bit easier to see them. Right, and past the asymptote as well, it's going to be negative here. So we sort of know that there's going to be sort of 2 branches to this function. Everything less than negative 2 is going to be one branch. Everything to the right of negative 2 is going to be the other branch. And if we quickly just determine the turning points of this function, so quickly using quotient rule here to differentiate it. So we have 3x squared minus 4 on x. So call this u, call that v, then the derivative is vu dash minus uv dash over v squared. So that's going to be, well, it's going to be x, derivative here is 6x minus, oh sorry, that's x plus 2. Minus 3x squared minus 4 times 1 oops, times 1 all over x plus 2 squared. Sorry, this is a bit messy. And just doing a bit of simplification, that actually ends up being 3x squared plus 12x plus 4 over x plus 2 squared. So then our intercepts will be wherever this quadratic equals 0, and we get, if we just solve that, then you get negative 2 plus minus 2 thirds of root 6. And then so your turning points are roughly at negative 0.36 and 3.6 something. So you can roughly do this because I'm just looking to see I'm just looking for the behavior of the function, right? So I know that there needs to be a turning point somewhere here, right? Because we go from positive to negative, then back to positive. So somewhere here, there needs to be a turning point. And also, and that needs to be a minimum, right? Because we can think about it as being positive, going from positive to negative, then back up to positive, it needs to be a minimum point. And on the left side, if we just test what that is, you can see that that's going to be a maximum. So there's going to be a maximum here on the left side. So now we sort of know a lot about the function, and I think we're ready to actually just graph it. So let's go ahead and draw a set of axes here. So inside a blank page, let's go ahead and insert our axes here. Oh, that's a bit bad. Don't mind the wonky lines. Right, so let's plot in our important point. So negative 2 is an important point because that's our asymptote. So let's just quickly draw that out. Let's also plot our oblique asymptote. So we had the line 3x minus 6. So it has an axis intercept at 2 here and at negative 6. So let's go ahead and, oops. I'll just extend this down a bit. Right, so also we have our intercepts like roughly here and here, and our y-intercept there. And our minimum to the function was somewhere in the negative area. All right, so just connecting the points, we know that it's positive here and it approaches infinity on that as we come across to negative 2 from the right side. So our function is going to look something like this, and it's going to approach our oblique asymptote. Oops. So its shape should be smooth. It should look something like that. Yeah. And then on the left side, remember we said we had a maximum, so it's going to look something like this, and it's going to approach both asymptotes as well. Let's just draw that out a bit nicely. Something like that. So it's not a great diagram, but you sort of see that function is going to look something like that. And that's how we graph that. So those are the techniques involved. So that's it for my components. I'm going to hand it over to Noah now, who'll go through the rest of calculus with you. So everything from polar coordinates up to integration. All right, thanks everyone. Yeah, I think, we'll take a break then.
Hey, how you going?
I'll give you my number, you can just do a call and I'll get your number that way.
That's
And thank you so much for this, it's really helpful.
okay.
The presentations are nice, and the guy yesterday as well. He was doing very well yesterday. Yeah. It was good. Thank you.
Okay, good job.
Sweet. You guys good to go, or do you need like a few more minutes? Up to you guys. Oh, sweet. Okay. Testing. Cool. All right. So I'll take the rest of the workshop. It'll cover everything from like hyperbolic trig stuff, bit of polars, as you can see there, and then also some you'll see just some like integral stuff, and hopefully it's not that bad. Yeah, and I think it's just best that we start. So why don't I start with polar coordinates? Basically, polar coordinates are a new kind of way of thinking, right? It's a way of moving from typical Cartesian coordinates like x, y to something that's defined in terms of distances and angles like r and theta. And the way in which we get these two identities is actually quite simple. So why don't we just take a look here at a xy axis in which we have something like that. And let's say we have some sort of arbitrary distance, which we'll call r, and some sort of angle, which we'll call theta. Okay? This distance here is x long, and this one is y tall. Fair enough. And so just using some like year 9 like SOHCAHTOA trig, what you'll see here is that cos theta is equal to adjacent over hypotenuse, so adjacent being x, hypotenuse being r, and then just multiplying by r, you get x is equal to r cos theta. And similarly with the y stuff, just using like sine, you're going to get sine of theta is equal to opposite over hypotenuse. And what you see there, multiplying by r again, you're going to get y is equal to r sine theta. Right? And this is quite convenient because you could just interchange the two, and you can actually solve a lot of kind of cool questions using polars, where in cases using Cartesians would be pretty hard. And you'll see this in some of the second year courses like MATH1131, when you're doing like lots of integrals and stuff. All right. Cool. All right. So find the gradient dy by dx of this curve, r is equal to 6 sine 2 theta, where theta is equal to pi on 6. So we have to take an x derivative of an r and theta function. So that can be quite confusing. And, you know, that's quite confusing, right? So we have to differentiate with respect to x of some sort of arbitrary function defined in terms of r and theta. And then you have to sub in theta is equal to pi on 6 after. So this can get confusing pretty quick. But we have to convert to polars. And then once you make the conversion to polars, everything sort of falls into place because you take away x and y essentially. So here's how we do it. Okay, so we have to find dy by dx. Now, what we essentially do is we use our identities from before. So we know that x is equal to r cosine of theta, but what's r in our case? R is its own little thing. So wherever I see r, I'm just going to chuck 6 sine 2 theta instead. So this becomes 6 sine 2 theta, and then whatever's left, cosine of theta. Okay. So that's great. I've got something in terms of theta now, which is kind of what we're after. So we know we're going to use thetas eventually. So why not get a function in terms of theta? We can take a theta derivative. So we can say the derivative of x with respect to theta. How should we do this? What rule you guys reckon? Well, probably product rule, right? You've got like two functions, and you can just u dash v, u v dash. And so what we get is we get u dash, so sine goes to cos, that's going to be 12 cos 2 theta, so that's u dash v plus u, so the original, times v dash, cos goes to negative sine of theta. Now, if you were to sub in, just grab your Casio and sub in theta is equal to pi on 6. I won't do the calculations in case I manually enter it wrong, but what you'll see there is that if you do it, you're going to get something that looks like this. So you're going to get 3 root 3 on 2, and that's going to be at theta is equal to pi on 6. So just trust me, chuck it in your Casio and you should get something that looks like that. All right. We also know that y is equal to r sine of theta, so something that looks along the lines of that, right? Okay. Now, what's r? R is, well, r, right? So wherever I see r, I'm just going to chuck in 6 sine 2 theta, and then just bang on the sine theta at the end. Again, y derivative with respect to theta, we can take dy by d theta, and try refrain from saying y dash, because you're going to see when I kind of manufacture my answer, expressing it like dy by d theta is actually quite convenient. And so what we get is, again, product rule. So u dash, that's going to be 12 cosine 2 theta times v plus u times v dash, which is cosine of theta. Cool. All right, so that's our y derivative with respect to theta. If you sub in pi on 6, which is what we're supposed to, theta is equal to pi on 6, what you'll see is you actually get something very convenient, and that is, I believe, 15 on 2. Okay, so I'm just going to circle these because they're quite useful. We're going to use these quite a lot. So we have y in terms of theta, we have an x function in terms of theta, but we have to find the derivative of y with respect to x. And the way in which we do that is actually quite simple, but it just requires a little bit of, chain rule. So dy by dx, what I'm going to do is I'm going to put dy here, and I'm going to put something that I can hopefully cancel, even though you're not really, but you sort of are, and then dx here. Well, two candidate options would be dr, right? But we didn't do a dr at any stage. So our only option is to just chuck in a d theta on both of them. So d theta, d theta. Okay, so we know dy by d theta is something that we've already calculated. That's just 15 on 2. And d theta by dx is something we don't have. So what we're going to ultimately do is, instead of writing it the way I did before, I'm going to divide by dx on d theta. Dividing by dx on d theta, timesing by d theta on dx, it's just the same thing, right? So what we're going to do is we're going to divide this by whatever dx on d theta was, and that was 3 root 3 on 2. Just using some simple algebra laws. If you want to divide fractions, you keep, change, flip. And so 2's cancel. And you're going to get 15 on 3 root 3. And I guess 15 divided by 3 is 5, so that's going to be 5 on root 3. You could leave it like that. Like, I think by university, they know that you know how to rationalize denominators. But, you know, if you're a stickler for the rules, why don't we just say 5 root 3 on 3. And that's your answer. So all that we did there is we found x derivatives in terms of theta, y derivatives in terms of theta,
find a way to like cancel the two rates, and just, yeah, it's just fraction simplifying after that. Cool. And that's how you do it. All right, integration. Cool. So here's a complicated theorem. It's not that complicated once you do an example, but essentially, I mean, I think you guys know this from high school, but you know, if you have like some sort of function, I don't know, something that looks like that, a, b, we can find the area under the curve by just integrating from a to b, and that will give you, you know, the area under the curve. And that's essentially what it's saying. That's mostly what we use integration for. You'll notice that if you take the derivative of an integral, right, you just get back to where you started, right? So like if f of x is your original function and capital F of x is your integral function, you can just differentiate again and get back exactly to where you started. Okay, cool. There's also this thing called the second fundamental theorem of calculus, which is essentially this diagram here, right? Where you take your integral function sub in b minus sub in a, and that will give you an area. All right, and so I thought I'd include this question actually because this is the sort of stuff you get tested on, not necessarily just integrating some sort of arbitrary function between a and b. A lot of the time, you're going to get something that's a bit more involved, and having done MATH1131, this is something you'd most likely get tested on. Cool. So how do you do this question? Well, number one, you might panic. Yeah, it looks pretty complicated, but there's actually a pretty nice way of doing these. And, you know, it looks difficult because, well, you've got an x derivative with a t integral. So what's really happening here? This function looks pretty difficult to integrate, if not impossible. Oh, maybe it's possible, but, you know, that would be a hassle to integrate. And so what we can do, essentially, is something quite nice. If you get an x derivative with a t integral, right, here's a cool little trick that you can use. Basically, your answer, just do this, really. Here's what you can do. Let me write it and then just explain it after. Ta-da. So that's what you can do. It's quite a cool trick, actually. And where's this from? I learned this from Milan Pahor's calculus lecture notes. I don't know if any of you guys watched his lectures, but that's just straight from there. So if you guys think I'm, you know, capping or something, you know, it's right there. Okay, so let's actually do this. So sub in the upper limit. So wherever I see a t, it's no longer t. It's going to be sine of x. So what I'm going to say is cosine of sine of x over square root of 1 plus sine of x. Oh, that's t squared, so square that one as well. Okay, times the derivative of upper. Now, here's sine x. What's the derivative of sine x? Anyone? Yeah, good. The same way sine goes to cosh, sine also goes to cosh. So while hyperbolic trig doesn't have any of the periodicity that regular trig does, its derivatives and stuff and its identities are very similar. Sometimes the same, sometimes very similar. A lot of the times you'll be like out by a negative or something. But, you know, there you go. Okay, so that's that part. Minus sub in the lower limit. So what do we get? We get cosine of 0 over square root of 1 plus 0 squared times, well, derivative, that's 0. So who really cares about that, to be honest? Okay. And what you might notice here is, any guesses on what that bottom one is? Yeah, good. And this part is cosh squared, well, square root of cosh squared, which just ends up being cosh, because we know that cos squared plus sine squared is 1, but in hyperbolic trig land, cosh squared minus, so you're out by a negative, but is that. And so what we see, if we make 1 plus shine x a subject, sorry, squared, you're going to get cosh squared x. Cool. And if we take the square root of that, square root of cosh squared is just cosh, right? So we're going to get cosine of shine of x over cosh of x. That cancels with cosh of x. And so your final answer is just cos of shine of x. Pretty cool. So a pretty tough question, right? You've got an x derivative with a t integral with x bounds. So, you know, pretty complicated, but that is a life-saving formula that you should definitely look into. Okay. All right. And there's some overly complicated notation which describes the same thing, but ignore that if you don't want to look at that. Cool. And there's your answer. Yeah. All right. Integration by parts. One of my favorites. Okay. So integration by parts, it's essentially like if you have two functions like banged together, the same way you'd like differentiate and use something like product rule, you can use integration by parts to essentially do the opposite with integrating like two functions like f of x, g of x together. Okay, so use integration by parts to evaluate this. Let me actually just create a blank page and just do it myself. So, all right. And in case you guys haven't seen another quick trick that I like to teach this with, I'll show you guys, but you probably already know it given you guys are smart people. So, all right, let's integrate this thing. We know that if we want to integrate by parts, we have the integral of u dv is uv minus integral of v du. The only question really becomes, what do I make u? What do I make dv? What do I make u and v and du? And that's kind of an exercise for us to solve. So what we do is, I like to use something called the Lie-8 principle when doing these. And basically that tells me what I should set my u to. So it's like an order of precedence, like the same way like, what they call like bod bid mass or something is like an order of precedence. So up first comes logs, inverse trig. Next is algebra, so like constants, x's, x squareds, x cubes. Regular trig, and the last one will be exponentials. And you'll be given, with integration by parts, you'll be given any two of them essentially, right? Because you've got like two functions like banged together. Okay, so what have we got here? Well, we have inverse trig, right? And we only have inverse trig. But technically we actually have something else. We have, that's really 1 tan x, tan inverse of x. So you technically have algebra as well. Okay, now why did I do that? Basically u is whatever the highest one was. So u is going to be equal to tan inverse of x. Now we want du by dx. Now don't write it as u dash, write it as du by dx, and you'll see why soon. So du by dx, just the high school identity, this is going to be 1 over 1 plus whatever your function was squared times by whatever the inside derivative is, okay? And then what we can say is du is equal to 1 over 1 plus x squared dx. Okay, so that's what we make u and like du. What about dv and v? So dv, now it's important that you start with dv and not regular v. So dv is basically whatever's left over, right? Whatever was left over. So we had that, and then we had that. Now integrating, and we get v, and then this one's going to be x. Don't write plus c, not just yet. Well, one, we've got a definite integral, so yeah, let's not go there just yet. Okay. And so what we can say is that our answer is equal to uv, right? So u times v, so that's going to be these two times together, so x tan inverse of x, right? And this is a definite integral, so we're subbing in root 3 and 0 minus the integral of v du, right? So x times du, which is 1 plus x squared dx. Okay. This one here, we can say sub in top minus sub in bottom. Subbing in the bottom is just going to get us 0, so we only really need to worry about subbing in the top. So that's going to be root 3 times whatever the inverse of inverse tan root 3, which I believe was, I think that was pi on 3, wasn't it? Yeah. So pi on 3, you just chuck that in your calculator, minus the integral between 0 and root 3 of this thing. And what you'll see is that the power of the top is 1 lower than the power of the bottom, so you can use ln. We ideally want the derivative on the top. So what I'm going to do is I'm going to manufacture the derivative to get it on the top. But then if I manufacture it, I'm going to have to find a way to then undo it again. So, right, just manipulating. And so what we get is root 3 pi on 3 minus 1 over 2. Once you have the derivative on the top, this is lovely. All you have to do is just ln bottom. And this is going to be evaluated between these two bounds. And so what we get is root 3 pi on 3 minus a half ln 1 plus root 3 squared, 1 plus 3, 4. Sub in 0, and you're going to get ln 1 over here. And so that's just a 0 term. And you know, you could simplify this to ln 2 if you want. You could leave it like this. And that's your answer. Okay. So that's how you do it. Now here's a question. We had like u substitutions and dus and stuff. How come I didn't actually change my bounds? How come I didn't change these root 3 and 0 bounds? Does anyone know? Well, the answer to that is that we're still in the x space, right? We haven't actually moved to like a new u space. We're still in the x space, so we can still use our x bounds. That's an important thing to note. That was something, because I didn't do 4 unit in high school, so when I was like trying to figure out why you don't change the bounds, yeah, that's why you don't, because you're still in the x space. You're still doing x integrals. You're not doing u integrals. So because you're still in the x space, you keep your x bounds, right? All right. Cool. All right. So, converging and diverging integrals. All right. So, here's some complicated theorems. Yeah, sure, you're welcome to look at them. But essentially, with these questions, you'll just need to say whether an integral converges or diverges, and then just provide some reasoning. We'll do all the reasoning in the example, so hopefully the theorems kind of eventually make sense after. Wonderful. All right. So here's an integral, a pretty complicated one actually, and we need to see if this integral converges or diverges. And when an integral converges, when you take the integral and like sub in the bounds, you're going to get some sort of like finite number, and if it diverges, it's going to be like infinite, and that will be a pretty good indication as to whether your integral converges or diverges. Now, let me actually write the answer. All right. So this integral, I mean, you could solve it, right? I mean, could you? It's pretty difficult. I don't know if there's an elementary function that sorts out an integral like this. But what I'm going to do is I'm going to look at a function that's less than it and see if that's greater than it, and see if that one converges or not. Because if you have something that's less than an already converging integral, then that one's also got to converge. So like if I've got like some sort of integral that like converges, right? Then any function below it will also converge, right? Because if the higher function converges, then the lower one also. So why don't I look at another function another integral rather, let's see if L converges, because if L converges, then K also does, because K is below it, right? Now, if we have something above a converging integral, that tells us nothing. If we have something lower than a diverging integral, that tells us nothing as well. But, you know, if it's lower than an already converging integral, then it also converges. So we'll use something called the comparison test, and I'll use another integral called L, and I'm going to say that this is the integral of something like that, and we've got to find something that's that's greater than that. And what I can say, or greater than or equal to, and so what I can say is, instead of 1 plus sine x, I'm going to say 2 on 3x squared, because if you look at this top one, right, that's always going to be less than or equal to 2, right? It's always going to be tucked in at least, you know, at or underneath 2, right? So if we can say that this integral converges, then something below it will also converge, all right? Nice. You know, there's a few ways we can do this. We can actually solve this integral because it's not that bad. So why don't we say this is equal to the integral, well, there's a few ways you can do this, but why don't we just do it like the more involved way, just so you can kind of see what's going on. So instead of subbing in infinity when we eventually do our integral, what we're going to do is we're going to do the integral from 1 to r of this thing, and then take the limit as r approaches to infinity. So instead of subbing in infinity, you're subbing in r and then taking r's limit as it approaches infinity. Okay. And this is going to be equal to the limit as r approaches to infinity of the integral 1 to r. Yeah, why don't we write this as 2x to the minus 2 on 3. I think that's legal. Yeah, it's fine. Okay. And what we can do is we can solve the integral. And so what we get is 2x to the minus 1 over 3 times minus 1. And we can evaluate that between r and 1. Or why don't I actually say x to the minus 1? Why don't I just say on x? Right, that's probably a bit easier. Okay, so this is equal to the limit as r approaches to infinity of, well, sub in top minus sub in bottom. Oh yeah, what's up?
Is it not x cubed?
X cubed, add 1 to the power. Where are we at? Well, that's x squared, so you integral, so add 1 to the power, divide by the power. Adding 1 to the power gives you... That's okay, not all good, I think. All right. And so what we get is sub in r, so you get minus 2 on 3r, minus sub in bottom, so 2 on minus, so that's really going to be plus, isn't it? So, oh no, hang on. Minus sub in bottom. Oh yeah, true, it is just plus. Cool. And what we get is, if we take an r limit, that's negative 2 over something massive, so that's going to be 0, and then this is just a constant, so that's 2 on 3. And because this integral dies down to some sort of finite number, most notably 2 on 3, we can say that it converges. Therefore, L converges. Which must also mean that K converges, right? Because if K is something below L, and L converges, then K must also. So yeah, this one converges as well. And you can do something called a P integral as well. I'm not sure if you've heard of P integrals, but if you have like a P integral, like something like this, you can say it converges based on the following criteria. Right? If you can find a way to construct a P integral, that's another way in which you can do it. Otherwise, you can do a standard improper integral, and instead of subbing in infinity, sub in r and then take the limit as r approaches infinity. Right. Cool. All right. Now for some implicit differentiation, also like logarithmic differentiation. And this is quite an interesting one because, I mean, you'll see soon, but that's like a pretty weird function to differentiate. But it turns out with some subtle manipulation, it's not the worst thing in the world. And what I'll do is take a look at this. All right. Well, I mean, there's a solution, but let me just do it. So we have y is equal to x to the power of sine x, and we want to find dy by dx. Okay. Yep. All right. Now, please don't use the power rule, right? Power rules are for constants, right? Like x squared, yeah, sure, bring the power to the front. Don't even think about doing that for sine of x, right? Not a constant, it's a function of x. So, well, what do? If you have like functions of x on the power, one thing that you can look into is logarithmic differentiation. So we're going to log both sides and then differentiate and then find a way to manufacture dy on dx. So what we're going to say is ln of y is equal to ln of x sine x. That becomes ln of y equal to sine x ln of x, right? Because with logs you can take powers to the bottom. Okay. Well, what do? It turns out if you want to do implicit differentiation, there's a way to do it using partial derivatives, partial derivatives you'll learn in 1b, but for now they kind of hide you from that theory. But here's the 1a way to do it. We can steamroll an x derivative on both sides. So what I'm going to do is I'm going to steamroll an x derivative on that side, and I'm going to steamroll an x derivative on that side. All right. Well, how do we take an x derivative of an ln y function? Well, what do, right? So what I'm going to do is sort out the side that I can sort out, right? The functions of x. This is going to be u dash v plus u v dash times 1 on x, so you can just chuck it on x. Okay, let me just double check that I did that right. I think it's fine. Yeah. Yep, so that derivative is correct. Now, how do I take an x derivative of ln y? What I'm going to do is I'm going to take a y derivative, and then what I'm going to do is I'm going to times it by dy by dx. And what that's going to do is think of the dy as like sort of cancelling. You're left with dx, but the advantage to that is now you can take a y derivative. So what we get is derivative of y with respect to y of ln y, that's going to be 1 on y, which we then slap a dy by dx on top of. And then that's going to be just what you see here. Amazing. Okay. Now we can isolate dy by dx simply by timesing by y, right? So get rid of the denominator by timesing it, and what we get is dy by dx is equal to y times all of this stuff. Right, but we know what y is, right? We made it very clear what y was. So wherever I see y, I'm just going to sub in what y is. And so y is equal to x to the sine x, so x to the sine x. Cool. And that's how you do it. So basically, log it, take derivatives there, and then you'll get a dy by dx, which you just make it the subject. You'll get a y function, just make sure to actually sub in what y is, and then you'll see that everything sort of falls into place. What a complicated derivative. Wow. Okay. All right. Last question. Cool. Now, we have something called hyperbolic trig functions, which I sort of touched on earlier, right? It's like, you can think of it as trig in the sense that it behaves very similarly. Like the derivatives are sort of similar. As I said earlier, you'll be out by like a negative a lot of the times, but sometimes you won't be. Sometimes the translation's like very clear. And a lot of the identities are quite similar as well. You might be out by a negative at times, but very, very similar. And the interesting thing is that if you actually graph these functions, I encourage you to just chuck this into symbollab.com. What you'll see is that they don't have any of the periodicity that regular trig functions have. They're defined in terms of e, so they've got all this weird non-periodic stuff. But it's interesting because the derivatives behave very similar to trig functions. And another significant thing of hyperbolic trig is in the field of deep learning, actually, if you guys are into like machine learning and like data science and stuff like that, the hyperbolic tan function's used quite a lot. You'll get into, if you're interested in the stuff, you might want to look at like activation functions in like deep learning. And the hyperbolic tan function is used quite a lot. And that's shine over cosh, so you can manipulate that. And so that's like a real world application. So this isn't just stuff that you're learning to prepare for an exam. It's stuff that actually has some contemporary relevance. But why don't we just narrow our focus down to Math 1A, and then I think in your own time you can see how these things are actually used in real world applications. All right. So there it is. So there's cosh x, again all defined in terms of e. So that's what it is. And shine x, very much the same. Instead of a positive, you just have a negative, right? So just remember that cosh is the positive one in the middle, and then shine has a negative. Tanch, you can derive by just taking shine over cosh, and you get tanch. Okay, very nice. And so what we're going to do is we're actually going to use that to find this integral. We're going to use the definition of shine and cosh to find this integral. And again, this is something, given it's an open book test, it's something you probably put into some sort of calculator, but there'll be intermediate steps that they'll ask you to like fill in assuming you're doing your exam on like, what do they call it, Mobius or something. Assuming you're doing your exam on Mobius, they'll ask for like intermediate steps. I think it's important that we just view the question like holistically rather than just merely the computation, because, I get that you can put this integral into some internet calculator and get your answer, but they will ask for intermediate steps, and that's why I think it's important that we go through that. All right. So this is some sort of quantity which we might want to actually look at in terms of E, because you'll see that it actually simplifies quite nicely. So what we say is that cosh x plus shine x is equal to, well, what is cosh x? Just that thing, so 1 over 2 e to the x plus e to the minus x plus shine x e to the x, and then that one's a negative, isn't it? Okay. We can then expand this thing, so this is going to be, right, that's what you're looking at, and this is going to be a half e to the x plus a half e to the minus x plus a half e to the x minus a half e to the minus x. Okay. And what you see here is that you get a half there and the things there which cancel, so we don't need to worry about that. Now, if we get a half of e to the x plus a half of e to the x, you just get e to the x. And that might be a question that you'll get on Mobius. You might get a question that says, this is like 1 on g of x, what is g of x? And you'll just say e to the x. Okay. And so now this integral is pretty simple, isn't it? Because this really, that's just a fancy way of saying e to the x. So what we're going to say is that this integral is equal to the integral between 0 ln 3 of 1 on e to the x dx. But that really, using powers and stuff, you can just say that that's e to the minus x dx. And what you get is just a 2-unit integral, isn't it? So what we get is minus e to the minus x, and we evaluate that between ln of 3 and 0. And putting this into your calculator, what you get is sub in x equals ln 3 minus sub in that, and you get minus 1 on 3 minus minus 1, and that becomes 2 on 3. Like that. Cool. And then they'll say, in the Mobius exam, they'll say, calculate like I, and then it'll be like, you'll get like a box, like I is equal to some sort of box, and you just type in 2 on 3. Yeah. All right. And that's pretty much it, right? So we had simplifying this. All you had to do was simplify that. That becomes e to the x. take an integral, sub in your limits, and that becomes 2 on 3. And I guess just to recap what we did there in that last part of the calculus section is, let's just go back. Yeah. So just to kind of recap, polar coordinates, x equal to r cos theta, y is equal to r sine theta, really useful identity. You're going to be using that a lot. And then that's kind of where we use it in this question. Another concept, fundamental theorem of calculus. You've got the first fundamental theorem and the second fundamental theorem. This was an application of the first. And while it looks scary that you have an x derivative in terms of a t integral, that formula comes to the rescue, and it becomes pretty simple after that. And then, yeah, complicated notation. Integration by parts. You guys might have your own way of doing it. I like to use the Lie8 trick. That helps a lot, finding like what to make u, what to make dv, and then just bang it together. Remember that we're still integrating in the x space, so no need for u bounds. Yeah, don't worry about that. So your x bounds stay the same. And then converging integrals, we can show that if a function greater than what we have is converging, then the other one also has to be converging because it's less than an already converging integral. And then if you can say it's less than or greater than an already diverging integral, then it's got to diverge as well. That's like the opposite, right? Then logs and exponentials, if you're taking a complicated derivative where you have functions of x on the power, you can use log differentiation to log both sides, use implicit differentiation. The way in which I did that was by steamrolling a dx on both sides, a d on dx on both sides, which you might have to patch up, but that's not a problem, right, because the dy's cancel. And you get something like that. Almost always you'll get like a y out the front because you're timesing by y, and then you just, instead of y, just write what y is in terms of x. And then hyperbolic trig functions. Here are two examples of hyperbolic trig functions, cosh x and sin x. Tanh x can be derived just by, one, memorizing, or two, just taking sin over cosh, the same way sine over cos is tan. And there should be, in your lecture notes, whichever ones you were given, like a whole list of identities that mirror trig identities very closely, but as I said, sometimes you'll be out by like a small negative somewhere. And the reason why this stuff is useful, one, because there's real world applications, and two, because you can simplify seemingly complicated integrals. And sometimes they might not actually be that nice. Sometimes on the denominator, they might actually write what cosh x is in terms of e, and you're just going to see e's everywhere and halves, and it's going to be very complicated. But just keep an eye out for that because, you know, a lot of the time, if the integral looks too hard to solve, it probably is just by looking at it. There's probably some sort of function of x that you can put there which makes it a bit easier. And that's really it. Now, that's it for the slides. If you have any questions for either myself or Lockie, now's probably a good time to answer it. But other than that, the MathSoc slides should be, well, the MathSoc slides here should be on our website. Otherwise, if they're not, just like bomb our email and just ask for them. But yeah, no, all the best for your exam. Online Math1131 exams are admittedly tough. I did it when they were online. It is complicated. I'm not going to sugarcoat that. But what really helps is knowing, especially your like hyperbolic trig identities, your inverse hyperbolic trig identities, which is sort of similar, and a lot of determinant and inverse stuff relating to matrices. So if you can memorize all your like determinant properties, matrix inverses, that goes a very, very long way. And then also, a thing to note in the exam is that, are they really going to make you write a massive proof? Well, maybe, right? We had one where we had like a text box and you had to like write the proof in like text, and like I didn't know LarkTech at the time, so it was very weird. But yeah, no, you might get a proof, so I know you might be thinking, oh, the exam's on Mobius, so I'm not going to get a proof question. I'm not going to worry about mean value theorem and stuff and proofs like Lockie did. My advice would be to still pay attention to that, because while you might not be able to write it properly, you'll have to type and like use some of the logic that you get from what like you showed you earlier on the earlier slides. Another tip would be, since it's open book, just make sure you have your notes with you, and well, if it is open book, I would assume it is. If it is open book, just make sure you have your notes with you, and also know exactly where to find the things that you're looking for. So know that, you know, if I go to this page, I'll be able to find, just like index it in your brain, really. And that's pretty much it. Also, just like breathe. It's not the end of the world. It's a first year university course. There's much bigger things in life to worry about. So, you know, obviously it's important, but there's more important things than your exam mark and more holistically like your WAM. But, you know, it's a really good starting block, Math1131. It's a great course. It teaches you a lot of like fundamental stuff that you'll use in a lot of like the second and third year math courses. But, you know, best of luck for your exam, and I hope everything goes well. So we'll probably end it there, and thank you very much. Adios. Should I stop the stream?